very important topic on industrial informatics and intelligence for vision-based industrial inspection. The motivation is on the Industry 4.0 about the digital transformation, which I will not spend time to elaborate. And that actually, Industry 4.0, and then now everybody talk about 4.0, including the agriculture 4.0, education 4.0, quality also have 4.0, which is the future quality under the context of Industry 4.0. And so today, I think the industrial inspection definitely is one very important component for quality control. And now the AI and machine learning bringing new opportunities. Here, I just list some. You don't have to read through that, but basically industrial big data plus AI tool bringing the new opportunity on all aspects in define, measure, analyze, improve, and control. Even though the thinking, the paradigm is the same, but the tool actually is being updating and become more powerful. So we need to go back and rethink our previous problem, see if any new solutions. So now we focus on the very specific problem on the industrial, the vision inspection. And what's the specific challenge? The reason I mentioned that is really the vision inspection it's been a very old topic that's been decades. No matter the hardware, software, or methodology have been studied for decades. However, still right now is a very important topic that we bring up to this shop. Now, here I use the defect inspection in printed circuit board as example, because later the example I show our partner is the flexible PCB company. Even though maybe this not as complicated as the other semiconductor company, but PCB can be a quite representative industry to show their challenges. Here on this PPT, on this page, I show both on data level and application level. For the data level, first is the diversity of defects. We actually have called interclass difference within for the between different type of defects, even though they are different. However, the difference very small, so very simple. It's very difficult to can find quite a diversity, quite different, and therefore it's hard to classify as the same defect. Later, I'll show you example. In summary, the diversity of the defects categories and features actually is pose a very significant challenge for us, even up to now, no matter how advanced your hardware and software is. The second is imbalance samples, which is fairly easy to understand, both at the level imbalance, the normal and the abnormal data, the size actually is quite different with very small number of the defect sample that we all know that. Also, there's an instance imbalance. When processed in segment, the scale of defects actually is too small compared with the whole image. Also, we have the category imbalance. Some type of defects we have more relevant, some are not so frequent, much less frequent. Also, we have the dirty data because it's related to labeling by personnel, not on purpose, but always had errors. And also there's variations in the annotation. Okay. Application level, the first, we actually expect the real-time performance with a very high precision. And so that's bring up the challenge that we need to calculate and then show result in a very short time, and also have the model generalization, because we have a different type of product and a different structure, even have a different structure, color, and the material, and each will bring in the different. So it's hard to use one model to fit all. So that also brings in the challenge. Here I show you some example. This is the data level. From the AOI, I refer that to the automatic optical inspection. in the process, as you can see, there are different type of the defects. Some are look quite similar. And then this page is on the product level. I mean, AVI. Sometimes because it's a final inspection, we refer that as the final visual inspection. So you can see there are different type of defects that all look quite diverse. So here I just show you example what I meant that the difference between interclass and intraclass. The interclass, there are different up for here, different type defects or for the vision machine. For intraclass, for the same defects, for example, short circuit, but look, the vision, the image can be quite different. Scratch, that can be different kind, the scratch. So even up to now, it's really difficult to be 100% or precisely to detect the defects at data level. Application level, here is showing the AVI products. They have a different kind of soldering mask. As long as it with different color, even though they all belong to different product, but it looks so similar. But even though they are similar, they are different. So you have a different kind of defects or different kind of product. You need to build a different model, and that bringing the change to practice. And therefore, we need research, and that's why we need this workshop. So I'll quickly go through this. The origin of our research team, actually, that was many years ago. We start from this statistical process control. I will not spend time on the literature review, but basically, originally this actually statistic process control has been one important topic and a tool for quality control. And this one, mathematically, we can, or statistically, we'll refer that as the change point problem. Somewhere in time, the one distribution changed to another distribution. We want to find out when that change happened and how much that happened in Y. But it's not just to have output, the process also input. Sometimes it's input and output, their relation, the function that matters. So we refer this as called profile SPC. And then fast forward to more recently, here is a change point model. At the same time, in computer science, they have anomaly detection. And then you can see their definition that look very similar. The difference is that anomaly detection is not limited to the change in this more like time series type of data. And the data are referred as image, picture, and even video and the other. Because of the tool has changed, so we are not limited. If we are not just limited our tool to statistic method, actually there are many other type of data we can handle and analyze. So if you generalize this, the framework is still similar, but it's a broader sense of the relation between X and Y that we can detect. And then we can bring in new tools and other than statistics or related to machine learning and AI model. And actually expand the recent years, my QLab referred to quality lab at HKUST. We doing the research in the anomaly detection and also the statistic process control, but more like a non-standard way of using that. And also we are interested in AI plus domain knowledge. It's not general AI, however, this method we focus on that combined with domain knowledge because we actually extend our research from statistics and industrial engineering. So the tool refer like a graph model and a causal learning, physics-informed AI, and they have a different tool but have a similar interest on combine the domain knowledge with the AI tool. One step further, more recently, AIGC, large language model, they also can bring in value to the research we are doing. For example, the multi-model data analysis. Before the time series or text or image, we need a separate model, but now we'll be able to combine them together and bring in the advantage. And also industry knowledge enhancement. Later, I will elaborate more on those the focus on bringing the quality large language, quality large model or industry large model that actually have advantage to handle multitask and cross domain. And I also have some collaboration with different colleagues on the industrial applications. For example, I work with my colleague in working visualization on uncertainty visualization, and also some colleague on industrial control code generation. And then you probably can see, even though the domain, the goal is similar, however, the tool become expanding beyond statistics, go to the AI tools, and therefore cannot just the research cannot be done just by one person. So that's a year ago. I established at HKUSC Guangzhou the Industrial Informatics and Intelligence Institute called III Institute. I collaborate under the institute. There's about 12 colleagues from different departments, from AI, data science, and also from smart manufacturing, robotics, and then we work together on mostly focus on industrial big data and industrial intelligence. Some recent result, and this is the one that the multi-model and the generative model in vision-based industrial inspection. This is the just at the starting early stage of a project. The focus on the thing we want to do, however, is still quite challenging to bring a multi-model generative model for vision-based inspection. The thing we propose, even at the first stage, is challenging to build a large database by metadata and the generative model. We are at this stage, at this point, bringing different type of data. If this one can be done, we still have even more challenges on the second step on the multi-model data alignment, how to align different modality data, and then so that they can be used together. We do have the solution in mind. However, it's really, we need to build on this step by step. And then later page, I will show you a little bit more detail. As part of its task, this is a paper actually being accepted in ECCV this year, presented in a different session. It's on the incremental unified framework of small defect inspection. And this one is focused on the dynamic update, the model based on new sample. How to do that? Because if you, for example, the small defects, actually the defect sample size is very small. Therefore, the original segmented space is somewhat overlap, and their feature conflict. And so if you allow them to have a new sample coming in, dynamic updating, incremental learning, they will cause a disaster. They will forget the previous feature. And how to do that? And we basically have a semantic boundary, and then we somewhat compress the non-primary space, and so that we can have we fix the updating space, and then putting some constraint for the new sample updating, for the dynamic, the incremental learning. As far as we know, this is the first article that provide methodology for the dynamic update for the new sample, focusing on the small defect inspection. And the overall picture, the thing we really want to do is this exciting project on to put all things together. It's industrial fundamental model for quality and reliability enhancement. I have to commit. Usually I present the research that we have done, but this one, well, it's just our proposal. We're working on that. This one is the overall picture, but in there are many subtasks that need to be done. The reason I present here is I hope that for those so many tasks, we can actually, if you are interested, we can work together. What I want to say is we will start from the specific domain industrial data. There is some open data if you cannot wait for the the industrial data to be available. And for specific domain fundamental model, there are several goals, and then if we get the data ready, the first challenge and the method is on the subdomain transferability. I think even though we try to have a quick start, focus on specific domain, but even for specific domain data, they have several subdomain scenario. Industry data is quite interesting. If you can collect the data you have, you just dump that in to build a model. It will bring in challenge because for example, even the same machine for different operations, the parameter, the model can be different. Even the same machine, the same type of machine for the same operations under different condition, the model, the parameter can be different. And therefore, we cannot ignore the unique thing, which is the domain knowledge. So how to bring in the domain knowledge to empower the pre-trained data set construction, that's very important because we find out the key actually is the construct the data set before we do the pre-training. So if we can get this done, we'll be able to build the foundation model pre-train. And then the next challenge is on the interrelated task information integration. This refers to the reason to make the industrial big model useful has many multi-tasks. We don't need to build many models for many tasks. However, one model for multiple tasks, this is not just a general scenario. The difference under the industrial context is that for example, for quality reliability, we do have many tests, but this is not just independent individual tasks. All these tests actually somewhat related. Also, they even in sequence. So how to make use of those information, interrelated information, to bring in for the fine tune, and I think that's will bring value. If we can have a good start, and then we can consider the cross-domain multi-model foundation model, bringing different model, and that will be the challenges on how to do the data fusion and the alignment. That's bringing another challenge. And then you want to really put in use, you need to combine with the industrial knowledge, rack system, and the industrial Q&A platform. Okay, I have a few minutes to wrap up and summarize. This final page actually inspired by the theme of the panel discussion, and then later probably I have a chance to elaborate a little more. But I want to quickly summarize that this is indeed a very important topic. Thanks for workshop, how to leverage the large model for the industrial inspection. The first is the key challenge. Key challenge actually including the diversity of the inspection task. Okay, there are several. I will not read through that, and also have the diversity of the data modality. So how to consider their difference and make use of that, that's remain a key challenge. And the challenge will bring in opportunities. The foundation model or the large model, what kind of opportunity they can bring in? The first we can think of is the enhanced detection accuracy, because we leverage the multi-model, not just one type model. And we believe before probably we only rely on sensor data or only rely on the image. However, if we align them right, I believe we can bring in more accuracy. The second is synthetic data generation, and that is something we cannot done before, but now we can solve the problem for small defects sample size. The third is assist the annotation is also a thing that the data labeling at the preparation of the data sets become easier. Strategic consideration is quite important to have value added because we need to determine how much value they can bring in from the large model. Before we use small model for all the tasks, it seems to work well. Why we need a large model? It's not just for fun, right? And then the second is the adaptability. I think right now the situation change become more dynamic, and we emphasize on customized manufacturing process, customized product, and the customer requirement also change. And then we cannot just keep build new model or new solution for different product and process. And therefore, I believe the one unified large model can handle different kind of task, and that will bring in value. And then also the unified model for multiple tasks, I believe will also reduce the system complexity and in terms of the management and the maintenance. So ultimately, I believe that will bring in good value, but still have the challenge to address, including the model paradigm choice. Before, most of statistic model is like pattern recognition model, but now it's generating model, so it's quite different. And how you align that within the industrial context remain a challenge. The second thing is a multi-task development. As I mentioned, all those tasks is not in the individual independent tasks. They're actually somewhat related. How to handle that simultaneously in the model, and that also remains a very challenging but interesting topic. The third thing is really ultimately want to implement the interactive paradigm that incorporate Q&A interaction to enhance the industrial decision, human-machine collaboration. I think ultimately make it useful. Okay, so thank you again, and I will stop here.